Mercury, Venus, Earth, Mars, all look like this. On Earth, that record isn't preserved because there's been wind erosion, water erosion, subduction, but on the moon, this record is preserved very well. And because we're able to study the moon in great detail, what we learn about the moon can also tell us about this early formative stage of planet evolution of the other rocky planets. Okay, so in the next slide here, okay, so this is how we make a map of the inside of the moon. We use radio signals, okay? Now, the interesting thing about how we do gravity at the moon is the way we usually do it, not with the moon, is we have a planet and we have the Earth. And spacecraft is in orbit around a planet, and we track the radio signal. And as the planet rotates underneath the spacecraft, we see how the spacecraft gets tugged out of its orbit due to gravitational changes. Okay. However, the moon is a special situation because we only see the front side, we never see the back side. So the moon never rotates, and we can never have a spacecraft where we can directly observe the back side. So what we do here, the way around it, is we send two spacecraft, and on the back side, they get to track each other. Okay. And so it's all these radio signals at different frequencies. Here, the Ka band is 32 gigahertz. And this tells us the distance between these two spacecraft. And this signal here at S-band basically calibrates the clocks between the two spacecraft. So we can see how fast these spacecraft are coming together and moving apart. And we can make this measurement to a couple of tenths of a micron per second. So we know in an absolute, we know where these two spacecraft are to about half the diameter of a human blood cell. Okay. So essentially all we're doing here is we're measuring the distance between 2 points, but we're doing it very, very, very well. Okay, next slide. Next slide here. Okay, so how are we going to do this? Okay, can you run this video? So, boy, I sure hope the sky looks like that tomorrow morning. This is a Delta taking off from pad 17. Not a cloud in the sky here. The spacecraft does a lunar injection burn, sets it off on its way to the moon. Then, if you like mechanical engineering, here's a nice send off one of the spacecraft, and then we wait about 8 minutes so that there's no interference, and then we send the other spacecraft off. The two spacecraft will deploy their solar panels so that they can get sunlight, and then they head off independently to the moon. Next slide. Okay, so when the Apollo astronauts went to the moon, they went there in 3 days. Okay, they did a straight shot out there. We wanted to get the humans there, get them on the surface, do their job, come home quickly and safely. But for the GRAIL mission, we wanted to do this more slowly. We originally did it to save fuel because we wanted to use small spacecraft. We didn't want to have to use 2 rockets to get these 2 spacecraft there. But then it turned out when we started looking at what I'll call here a low energy trajectory. So we send the 2 spacecraft here, one is in yellow, one is in aqua, out to the Sun-Earth Lagrange point, which is essentially a place where the forces between the Sun and the Earth vanish. So it's like a buoy in the ocean. And we send the spacecraft out there, they zing around, they take 3.5 months to get to the moon. And this has a whole lot of advantages. So first of all, it allows us to insert both spacecraft into orbit around the moon a day apart, so we're not doing 2 critical maneuvers on the same day. It allows the spacecraft to degas, and gases coming out of the fiber of the spacecraft actually mimic gravity, and that's a bad thing, so we want the gases to come out before we get there. It also allows us to completely decouple our operations during cruise from operations around the moon, which simplifies the situation for us. And so these 2 spacecraft will arrive at the moon no matter what day in the launch window we launch. They arrive New Year's Eve and New Year's Day. Okay, next slide. Okay, so then the 2 spacecraft, they arrive a day apart, if you could run this video here. And they will go into independent orbits around the moon, polar orbits, a little bit more than a series of very small thruster maneuvers will take place to take energy out of the orbit, which brings the apoapsis, this far part of the orbit, in, and circularizes the orbit about 55 kilometers above the moon. And this is the orbit that we want to map the moon at. Next slide. Okay, so then this is the way the two spacecraft operate. This is also a video, if you can bring that up. So the two spacecraft are now in orbit around the moon, 55 kilometers above the surface and between 60 and 225 kilometers apart. And you're going to see here how we do the ranging. So they're in polar orbit, one's chasing the other around. And you're going to see here in a second in the video the basic measurements. So here we have an extra mass here, and so this spacecraft here senses it and speeds up because there's an extra mass, and it causes the distance between the two spacecraft to increase. And then this one starts to sense this mass, so it speeds up, catches up to the first one, and so essentially the two spacecraft do a dance in orbit around the moon as they're making all these measurements, going over craters and underground features. Okay, next slide, please. Okay, and one of the things I'm extremely proud of about this mission, because I'm a teacher and I greatly value education, is we have a camera system. Each spacecraft is carrying 4 cameras that middle school students are going to be able to target images on the moon. So this experiment is called MoonCam. It's led by Dr. Sally Ride, who was America's first woman in space. It's the first time an imaging experiment on a spacecraft has not had a scientific purpose. It's devoted fully to education. And so we have these cameras that are mounted on the spacecraft. And then the next slide, please, which I think is the last one. So students will be able, they need to learn how to use the targeting software. It'll show you where the two spacecraft are going to be at a given time, and the students can propose images, and these commands will be uploaded to the spacecraft by undergraduates. And we've just released an app for the mission. It's downloadable, free on iTunes, where you can check the countdown of the mission. And once the two spacecraft get into orbit, we will load the students' MoonCam images up there so you can see them, and you will also be able to also put the software on there so that at any given time you can pull out your app and see where the two spacecraft are in orbit around the moon. So we're very excited about this educational opportunity that we're going to provide. So that's it for me. Thank you very much.